Have you ever looked up at the night sky and felt a sense of profound wonder? A feeling of connection to the vast, silent universe? In that moment, you're not just seeing light from distant stars, you're peering back through time itself. It's a humbling experience, a quiet reminder of our small place in a grand cosmic ballet. From our vantage point, we see the familiar celestial bodies, the steady glow of the moon, the predictable wandering of the planets, the distant shimmer of countless stars. Everything seems to follow a set of rules we've worked for centuries to uncover. The elegant dance of gravity, the clockwork precision of orbits, it all seems so peaceful, so perfectly orderly. But what if I told you that this cosmic serenity is a fragile illusion? A thin veneer of predictability hiding a much deeper, unsettling reality. What if there are places out there, not in some distant galaxy, but right here, orbiting the same planet we call home? Places in our own celestial backyard that are deeply, fundamentally strange, where the known laws of the universe seem to bend or even break. These are places that defy our understanding of physics, challenging our sense of safety. For decades we've been picking up faint signals, whispers of phenomena we are only just beginning to comprehend. Data streams that inexplicably corrupt, instruments that register phantom particles. These aren't just random errors, they are patterns, secrets hidden in the cold, empty darkness between the stars. With characteristic confidence, we send our most advanced probes and our bravest explorers into this great unknown. We shield them, we build in redundancies, we equip them with the best technology humanity can create. We believe our engineering can conquer any challenge the void throws at us, mapping their trajectories with absolute precision. But space has its own rules and its own dangers, many of which remain invisible to our eyes and instruments. We've learned to protect against the obvious threats, the crushing vacuum, the extreme temperatures. But other dangers are far more subtle and infinitely more mysterious. They aren't physical obstacles, but fundamental inconsistencies in the environment itself. We call them anomalies, glitches in the very fabric of space-time that hint at forces beyond our grasp. What happens when hardened spacefaring computers suddenly crash for no reason? When navigation systems report an impossible location? What happens when our astronauts report seeing flashes of light inside their own eyeballs, things they cannot explain? This isn't a distant threat, it's a clear and present danger, waiting silently in orbit. Are you ready to look into the abyss? Space isn't as empty as it seems. Hidden dangers lurk in the void, and one of the most notorious is right here hugging our planet. This place has a name, though it's not one you'll hear in casual conversation. Scientists call it the South Atlantic Anomaly, or SAA. The term anomaly is a clinical understatement for a region where orbital safety rules break down. The name might sound harmless, a mere statistical blip. But for engineers and astronauts, this blip is a monster, an invisible predator stalking low Earth orbit. It's a vast, invisible domain of peril, larger than the United States, stretching from South America across the Atlantic toward Africa. This is a zone of intense, high-energy radiation, a storm of trapped particles looming over the planet. So what creates this treacherous region? Our world is constantly bombarded by the solar wind. Earth's magnetic field deflects most of these energetic particles, creating a protective bubble. It also traps particles in donut-shaped zones of intense radiation, the Van Allen belts. The SAA exists because this shield isn't perfect. Our planet's magnetic field is tilted and offset from its geographic center. This creates a dent, where the inner Van Allen belt dips unusually close to the surface. It swoops down to just 200 kilometers altitude, into the paths of countless satellites and the International Space Station. Astronauts passing through report seeing strange flashes of light with their eyes closed, a direct effect of radiation on their optic nerves. Inside the anomaly, radiation can spike 1,000 times higher than elsewhere in orbit. For any spacecraft, passing through is like running a gauntlet. High-energy particles pierce hulls and slam into sensitive electronics. They cause single-event upsets, flipping digital bits from 0 to 1. This can corrupt commands, scramble data, and trigger system failures. These upsets can force systems into safe mode, cause permanent damage, or end missions. Japan's Hitomi satellite was a high-profile victim, lost after a chain of failures likely initiated within the SAA. Consequently, agencies meticulously plan around it. The Hubble Space Telescope, for example, powers down sensitive instruments during every transit. This precaution creates recurring data gaps, blinding our premier eye on the universe for up to 15% of its time. And the problem is evolving. The anomaly isn't static. It's drifting westward and expanding. Recent data suggests it may be splitting into two lobes, making this dangerous region even more complex and perilous. This evolution raises urgent questions. Why is the field weakening here? Is this a sign of a future magnetic pole reversal? And what does it mean for our increasing reliance on space? For now, think of it as a low-hanging cosmic power line, sagging dangerously close. It's invisible and silent, but buzzing with a deadly energy that poses a constant, growing threat right above our heads. The South Atlantic anomaly has earned a chilling nickname, the Bermuda Triangle of space. These aren't myths. They're documented technical realities. In 1974, Skylab's main computer crashed during an SAA pass. The crew scrambled to regain control. Over the decades, the Dragon has claimed many victims. Japan's Hitomi X-ray Observatory spiraled into failure after a suspected single-event upset. Even laptops aboard the space shuttle would crash during SAA passes. Crossing the SAA can feel like Russian roulette with billion-dollar equipment. Invisible particles, silent threat, very real consequences. Spacecraft walls shield a lot, but not all. High-energy protons can pass through equipment, walls, and even the bodies of astronauts inside. They report mysterious flashes, even with eyes closed, cosmic rays triggering the retina like silent fireworks. Each particle that paints a flash also traverses other cells, brain, DNA, adding to cumulative risk. NASA tracks dose with dosimeters and adds shielding in key ISS areas. Yet the risk can't be erased. It's part of living and working in space. There are whispers of events far harder to explain, ghosts in the machine, equipment seemingly operating on its own during SAA transits, commands executing with no human input. Officially, radiation. But to witnesses, it felt eerily purposeful. Satellites roll power instruments or spit gibberish right inside the SAA, then leaving the zone, many simply recover. It blurs the line between predictable malfunction and something more mysterious. Perhaps no instrument shows the SAA's impact better than the Hubble Space Telescope. At about 340 miles up, Hubble passes the SAA several times a day, and must shut down for 20 to 30 minutes each time. Roughly 15% of its orbit is lost. Its detectors would otherwise be peppered by a hailstorm of protons. Astronomers plan around SAA blackouts, sometimes missing fleeting transients, a supernova, a gamma-ray burst. The anomaly acts like a cosmic sensor, dictating what we're allowed to see. A humbling reminder, our quest for knowledge is at the mercy of nature. We don't have all the answers. The story of the South Atlantic anomaly doesn't start in space, but thousands of kilometers beneath our feet. It's born deep within our planet's outer core, a turbulent ocean of molten iron. Here, immense convection currents churn this liquid metal, and this colossal engine, the geodynamo, generates the magnetic field that has protected life for eons. But this engine isn't perfect. Seismic tomography has revealed two continent-sized blobs of dense rock at the core mantle boundary. These LLSVPs disrupt the smooth flow of the molten core. Scientists believe the massive blob beneath Africa is the primary culprit, warping the magnetic field directly above it. This disturbance propagates outward, surfacing as the South Atlantic anomaly. This local weakness is part of a larger, alarming trend. Earth's magnetic field has been weakening for centuries, losing nearly 10% of its strength. As the global shield thins, the SAA has not only grown in size but has also deepened, becoming an even more pronounced vulnerability in our planetary defense. This has led some to a chilling speculation. Are we witnessing the early stages of a geomagnetic reversal? A complete flip of our planet's magnetic poles. Geological records show these reversals have happened many times. During the transition, which can last for thousands of years, the field becomes chaotic. The overall shield could weaken to a fraction of its current strength, leaving the entire planet far more exposed. The SAA may be a terrifying preview of this future, a localized glimpse of what it's like when our planet's magnetic armor fails. If this weakness spreads, the consequences could be catastrophic. Unfiltered cosmic rays would bombard our delicate web of technology, satellites, navigation, even power grids on the ground. The long-term effects on climate and life itself remain a profound unknown. For space agencies, this is a daily operational hazard. It is, without a doubt, NASA's darkest and most persistent secret in near-Earth space. We chart comets and read galaxies' light, yet the SAA humbles us. It is untamed celestial wilderness hovering over our world, where rules change and risks multiply. a weakness, a dent, perhaps even a portal to a more hostile reality. If our planet hides such a secret, what darker mysteries wait for us in the vast silent emptiness of space?